Right? Good morning, and so this is joint work with Ridi Basu and Jonathan Hakmon, who are both grad students here. Let's see, Ridi is here, and so let me tell you what this is about. So first, just to fix the notation, we're going to have a reversible and irreducible transition matrix P. Pi will be the stationary distribution. Reversibility means that moving forward or backward in time, you get the same distribution when you start at stationarity, and this is the usual detailed balance formula which captures that. And to avoid periodicity issues, we'll look at lazy chains, so that stay in place with probability at least a half. There are other devices to avoid periodicity. This is the simplest one. And as usual, we'll measure distance to stationarity and total variation distance. So the maximum of the difference in probabilities between two measures. And d of t is the maximum total variation distance at time t. So this is the maximum over all target sets A and initial points X of the difference in the probability you are at A versus pi of A. Okay, so d of t is really measuring your distance to stationarity in the rather demanding way, maximizing over starting point and target sets the total variation distance. And so the epsilon mixing time is a time when this is below epsilon, and this d of t is a monotone decreasing quantity, weakly decreasing. So after that time, you really are less than epsilon. Now, the distance to stationarity has a submultiplicative property, which means once it's really strictly below a half, it continues to go down. So if you don't care about constants, then you can just fix the constants that depend on epsilon, then you can just fix the epsilon to be a quarter. But here we'll want to do finer things and not really understand the dependence on epsilon. But just, T mix is just going to be abbreviated, an abbreviation for T mix of a quarter when we don't write the epsilon. Okay, so what does cutoff mean? Maybe I'll show this first in the picture and then go back to the formula. So when we look at this function d of t, and I write dn of t because typically we have a sequence of Markov chains on growing graphs. So n is the parameter here. And the structure of d of t is once it gets strictly below a half, it has to go down exponentially, but actually the decay could be much faster than that. And this is when we have cutoff. So just to contrast the two examples that we think of the most, if we have a cycle, there's no cutoff. So on a cycle of n points, when we run a lazy random walk, the mixing time is order n squared, but there's really no distinguished constant that multiplies this n squared. That is, what constant times n squared depends on how precise you want to be, what the epsilon is. So as you decrease the epsilon, you need to run larger and larger constant multiples of n squared. There's no magic constant there. On the other hand, if you look at our other favorite example, or even more favorite, the hypercube. So what is lazy walk on the hypercube? It's a very, very simple object, right? You have, let's see, where's the eraser hiding?
It's attached to the board.
Attached to the board, thanks. So, so if we are looking at the hypercube, the simple random walk on the hypercube is right. So we have n bits that represent our current position in the hypercube. And what is lazy simple random walk? One step is you choose a coordinate at random, and you don't necessarily flip it, you randomize it, because we're doing a lazy walk. So you replace this bit by a random bit. Okay? So that's a pretty simple process. Who can tell me what the mixing time is? How long till you mix? So you have n bits. Each time you choose a bit. uniformly at random, and you replace that bit by a random bit. When are you going to get close to the station distribution? What?
You just have to hit every bit.
You just have to hit every bit. So that's coupon collectors, that's n log n. Is that the right constant? Well, it is the right constant for hitting every bit. So n log n is coupon collector, but it's not the right constant for our problem here, the mixing time. The right constant is half. So half n log n. Why is that? Suppose, let's go to, to 0.51 n log n. So what happened? We haven't hit all the bits. There's a little less than root n that we haven't hit, like about n to the 0.49 that we haven't hit. So so if we look at time t, which is 0.51 times n log n, then there's some subset here that we haven't hit. It's relatively small. It's n to the 0.49. The 0.49 has a plus little o of 1 there, but okay. So that's the set we haven't visited yet. So that set should actually has the initial setting, whatever we were at. But the location of that set is completely uniform and random. So here's a little observation you can easily prove. If you take a vector of n bits uniform, and you pick, which is really completely mixed, and now you pick a random subset there, but it's small, it's below noise level, it's below root n, so it's n to the 0.49, and you just change all those, say, to zeros. That's still indistinguishable from uniform. It's an easy thing. So it's, you can think of it various ways. One way is that, the binomial distribution is pretty flat near the top. So if you move by less than root n, you really can't tell. So the mixing time is half n log n. So, and that doesn't depend on the epsilon. So T mix of epsilon is asymptotic. So here's what happens on the hypercube is for any epsilon in 0, 1, T mix of epsilon is asymptotic to half n log n as n tends to infinity. And I should put an n here, so this is on the n-dimensional hypercube as n tends to infinity, and this doesn't depend on epsilon. So epsilon only affects the next order term, which is order n. If you're trying to, for the hypercube, one can do the analysis to arbitrary precision. It has been done, but we just want it as an example here, and this is kind of surprisingly, this is the second example of cutoff. This was done by Aldous in '83. The first example is actually harder, and it is random transpositions. I'll tell you about it in a moment. Okay, let's go back to the formula. So formally, what does cutoff mean? It means that T mix of epsilon has an asymptotic that doesn't depend on epsilon. So one way to say that is T mix of epsilon minus T mix of 1 minus epsilon is asymptotic. Well, this is little o of T mix. Okay. And here I wrote T mix, this is T mix of a quarter, but it doesn't matter which constant I put here and there. So T mix of a quarter or T mix of 1/8, they're all within a bounded constant of each other. So there it doesn't matter. But we want that this difference is little o of the variables, which really is equivalent to this picture of the total variation distance going down quickly. And more formally, you can capture how large this is by kind of a window. So for the hypercube, the window is size n. That's what I told you. So when you vary epsilon, T mix of epsilon only changes by order n, as opposed to its order is n log n, but it varies only by n. So in other words, if you look at this graph of T and of T, if you put a window here of width C epsilon n for the hypercube, then you'll go from 1 minus epsilon to epsilon within this window. Okay, so this for the hypercube is this T mix is n log n, and the window, which is smaller, n order n, suffices to do all the action as far as total variation goes. So just to say something about the motivation, why do we care about cutoff? Let me quote Dan Arundel, who said that, once I was told I just need to know if mixing time is polynomial. Then people told me, well, the power is kind of important. Then I was told to try and see if there's a log term. And now they want me to find the constant. I mean, so it's not that we're so obsessed with the value of the constant, but sometimes we are. But the cutoff has a real meaning. It captures some high dimensional behavior, and this is something we're still struggling to formalize, but there are now many theorems in this direction that say, mixing can occur for different reasons, and the hypercube is one case where mixing comes from, a lot of things have to kind of mix. You have a lot of independent components, and enough of them, except for, up to a noise term, they all have to kind of be randomized. The other extreme example is actually not the cycle, but this example of two cliques. So you have, two copies of Kn. Remember, we're doing lazy walk, and there's an edge between them. So the random walk here will walk. So mixing is really corresponding to having a reasonable probability to cross from left to right. Now, the event of crossing from left to right, it will take time n squared, because you have to visit this vertex, which happens only one in every n steps. But then when you're here, there are n vertices pulling you back and only one way to cross. So you only have probability 1 over n to cross. So it will take you time n squared to make the crossing. But you cannot say which constant times n squared. Is it 1 n squared, 2 n squared, 3 n squared? It's actually an exponential variable that governs, the multiple of n squared. And so so mixing occurs here from waiting for one rare event. So at a very rough scale, which doesn't capture all examples, we could say that non-cutoff corresponds mostly to examples where we have to wait for something, for kind of one rare event to happen, while cutoff corresponds to a case where lots of things which are weakly dependent have to go right. And so I made several conjectures in this direction back in more than 10 years ago, and one of them is that kind of in models where you have a graph labeling, if you are at some kind of high temperature, if the vertices are weakly correlated, then you should have cutoff. And this, for the case of the Ising model, has had a spectacular proof by Alan Sly and Eyal Lubetsky, series of great papers that say in the high temperature Ising model, on lattices and many other graphs, you have cutoff. Okay. So the first example, what was the first example of cutoff? It was actually Diaconis and Shashahani in 81, random transposition. So you have n cards. They didn't do a lazy chain. They did the following. You have n cards. The left hand chooses one card, the right hand chooses another card, and you transpose them. So you might choose the same card in both hands. And so what's the mixing time here? Well, here you actually have to touch basically all cards to mix, because a random permutation just has in expectation one fixed point. Right? So if you have a large number of fixed points, you're not mixed. You can't allow root n fixed points. You can't allow even log n fixed points. You really have to get the number of fixed points down. So you have to touch all cards. Each time, in random transpositions, you are usually touching two different cards. So that gives you a lower bound of half n log n. Now it's non-trivial that that's actually sharp. So it's again half n log n for random transpositions. They proved it using representation theory. There's actually no simple probabilistic proof. It took a long time to have a nice probabilistic proof, but now there are some nice ones. One was found by Berestitsky, Schramm, and Zeytouni a few years ago. But no proof is very, very simple of this upper bound. Anyway, that's the first example of cutoff. It was still half n log n, and again, intuitively, there should be a simple explanation, because again, there are lots of things that have to go right. A lot of cards, and basically they all have to be randomized. But this simplistic view has not been enough to prove things. And there's an influential paper in the Monthly by Aldous and Diaconis 86 where they emphasize the problem of understanding when you have cutoff and when you don't, and they coined the term there. Okay, so, well, this is a spectral graph workshop. So this is 1 minus lambda 2 is a spectral gap, and following Aldous, we'll use the relaxation time notation for the inverse gap. Okay, so what does intuitively so we know what the gap means formally, but what does it intuitively mean? How is it related to the mixing time? So for instance, in the hypercube, the relaxation time is n, while the mixing time is n log n. So what does the n really mean? You can think of it as if instead of starting in a fixed state, I know that I start in some distribution that's spread over, say, half the hypercube, and I went to ask, when does that get close to the stationary distribution? Then it's only the relaxation time that matters. So, but when you start from a 1 point, there's you have to get out of that corner, and this is actually what we're going to emphasize here. So here's one condition which is actually easy to see that it's necessary for cutoff. So the relaxation time should be little low of the mixing time, or equivalently, the spectral gap times the mixing time should go to infinity. So it's easy to see if this fails, you cannot have cutoff. So if the relaxation time and mixing time are the same order, then there's no cutoff. And so this is, for instance, what happens in the cycle. Both are order n squared. And the reason is that you have an obstruction, which is the second eigenfunction. That is, if you take the stationary distribution and just perturb it by some multiple of the second eigenfunction, that perturbation, just doesn't die out by the relaxation time. It gets scaled down, but just by like a factor of e. So you start with stationary, you have the stationary distributions, okay, and you perturb it by the second eigenfunction, okay. So you have this. So say the stationary distribution is uniform, and then you perturb it by some multiple of f2. Now, how much does f2 go down? Well, it changes by a factor of lambda 2 in one step. So by the relaxation time, it will change by factor lambda 2 to the power t rel, and this is about 1 over e. Okay, so this perturbation by the relaxation time goes down by a factor e. It doesn't go away. So if I wait for 100 times the relaxation time, I'll just go down by a factor e to the 100, which is still just a constant, and so the perturbation doesn't go away. So I cannot have cutoff, because if I make my epsilon less than e to the minus 100, then then 100 times the relaxation time is not good enough. So it's evident that this is a necessary condition for cutoff, and in
question, sorry.
Yes.
So one way the mixing time and relaxation time interact is you pay a start penalty. So if the lowest probability, steady state probability of a state is little over 1, is that enough to say that in that case the bounds we can prove on mixing time are bigger than the bounds we can prove on relaxation time, at least upper bounds? Is it true also that that's tight? I mean, so I tell you that some states steady state probability is going to 0.
Yeah. Then look at the cycle, right? So all steady states are going to 0, but there's no cutoff.
I see.
Or look at these two cliques again. So I'm not really looking at graphs where one state has a sizable probability. So you can.
They're spread out. I mean, each state.
Things are spread out, but still, so cutoff doesn't. It's not that.
Not that
so okay. So this is I think condition for us, and somehow in all nice non-contrived examples, it's also sufficient for cutoff. But there are these examples. So this condition is not equivalent to cutoff, and kind of the challenge has been and still is to understand, well, what do you need to add to this to actually get cutoff? Now, one thing, this is a really, you see, cutoff, if you have a lot of symmetry, you can diagonalize things and check cutoff. That's how it was done in the early examples. And then if you have other structure, like the Ising model with weak dependence, then there's other techniques. But in general, it requires very precise understanding. Now, this condition, T-rel little o of T mix, is much more coarse because it's enough to estimate both quantities up to constant. So if this was sufficient, then we'd be in a happy state. It's not. So we ask, is there something else which is checkable, and we can add to it and make and derive cutoff without actually calculating the constants in the mixing time. So there are, some examples that show this is not sufficient due to David Aldous and Igor Pak. I'll show you Aldous's example in the next slide. So here's an example. So there's a path of length. Here we made it 10n, but there's some flexibility. And on this path, you go right with probability 1/6, left with probability 1/12, and it's very lazy. Stays here with probability 3/4. And then it gets to this point here with probability half, it goes up or down. And then you basically have the same chain on the bottom and the top, but on the bottom it's half lazy. And so every time, if it moves to the right with probability 2/3 and left with probability 1/3. But here it's lazy with half, here it's lazy with 3/4. So if you look at this chain, what is it? How is it behaving? It's going to. So it's easy to see. This is the worst point to mix, and almost all the stationary distribution grows exponentially as you move from left to right. So almost all the stationary distribution is in a small neighborhood of this vertex. And the mixing time is very well approximated by just the time to go from x to y. But that time as a random variable is not concentrated because there's a decision point here, and you might go up or you might go down, with probability half. So you might reach from this side or from this side, and it will take you, this is going to take you 120 n, so that you move at speed 1/12 here. And then on the top, it's going to take you another 12 n. And if you choose the bottom route, it's going to take you just 6 n to go left to right. So there's, you get different constants, so there's no cutoff. So in particular, if I look at two intermediate numbers like 130 and 128, in both of them, the total variation distance is bounded away from 0 and 1. And so there's no cutoff. Here's a picture of how the total variation distance looks as a function of time. So it's very close to 1 until this time, 126n. Then there's some chance you've mixed because there's some chance, I should say you're mixed. You get much closer to the stationary distribution in the sense that all the paths that chose the fast route, have reached the right-hand side. But then it takes until 132n before the laggards get to the target. And so this is the structure. So this is not cut off. Okay, any questions? So this is, on the other hand, this is a weighted expander. So if you look at this graph, because I said almost all the stationary distribution is here. So if you have a set of measure less than a half, it must miss either this, basically it must miss y. Y has about almost half the stationary measure, or it must miss y or one of its neighbors, and then you usually see that you have the property of a weighted expander. So this has a spectral gap that's bounded away from 0 as n tends to infinity. So the relaxation time here is order 1. And you can also think of it, if I'm starting in some distribution which has not concentrated a point, but rather on a large set. Now large in terms of the stationary distribution. So that distribution has to have some mass around here, very close to the target. And then it's going to mix immediately. So the relaxation time is little o of the mixing time. The mixing time is large here, it's linear in n. Yet there's no cutoff. Now, okay, so we want to capture what's bad in this example.
You have an example of a reversible chain?
This is reversible. Yeah. So that's the whole point. So the stationary distribution just doubles every time. So here we just added more laziness, but it doesn't affect things. So that's the whole point. I'm just talking about reversible chains. Okay, and Pax examples are also reversible, and they are actually more symmetric. We still don't know. Here's an example where we don't know whether the conjecture holds. Take a transitive expander, so like one of these famous Lubotsky-Phillips-Sarnak expanders, any Cayley graph which is an expander. So on an expander, we know the relaxation time is order 1, the mixing time is order log n. So I conjecture that transitive expanders all have cutoff. So this is bounded degree transitive expanders. Conjecture they all have cutoff. But we don't know a single example where the answer is positive. We don't know a single example where the answer is negative, which is transitive expander. If you drop the transitivity, then there are examples going both ways. So, okay. So the key here will be to go from mixing time to hitting times. So the hitting time of a set is in some ways a simpler quantity. We don't ask for the exact distribution. We just ask, are we there yet? And so there was one relationship between hitting and mixing that was already found by Aldous in the 80s, but this was harder to use because it involved hitting times of sets of unknown size. And so in 2011, there were two independent works, one by Oliviera and one by myself with Susie, where we showed that actually up to constants, mixing time can be characterized by hitting times, but there's a catch, it's hitting times of the worst set. So if you look at the maximum over all sets bigger than alpha, and you fix some constant alpha less than a half, and you look at the maximum expected hitting time of such sets, you fix the alpha and you look at the max. This is equivalent to the mixing time up to constants. So it's another way to think of the mixing time, which is, sometimes useful. But this is up to constant. Okay, so it's not going to give you cutoff. Okay, so by the way, this is an example that shows that, so it said we fix a constant alpha, alpha has to be at most a half. If we talk about hitting times of sets and we require them to be bigger than a half, then the equivalence breaks down. Like in this example of the two cliques, the mixing time is n squared. But if I take a set which is strictly bigger than a half, it's going to have representatives on both sides. And so wherever I start, I'm going to hit it much faster in order n or even order 1 if it's substantially bigger than a half. So, well, the mixing time is n squared here. So it's really a delicate point. It's important that the target sets that you look at are at most a half. But why is it important in this example? Because this example, the product condition fails. So the relaxation time and the mixing time here are both n squared. So one thing which is crucial is if you have the product condition holding, so the relaxation time is little o of the mixing time in the sequence of chains, then it turns out that the equivalence is much sharper. There's no loss of constants, and you're allowed to take very big targets almost a full measure. And what this means is that the mixing time can be related to escape times or expansions of very small sets. So I'll come back to that at the end. So it's really, you need to control just two things, the time to escape from tiny sets and the relaxation time, and you know the mixing. Okay. So this general question I mentioned was first understood by, in the very simple case of birth and death chains. So birth and death chain is just a nearest neighbor random walk on a path, but we're allowing arbitrary transition probabilities. They're only to neighbors. And remember, we're making it always lazy to avoid periodicity. So this is a birth and death chain, really a special kind of chain. But for these chains, it is true that relaxation time, and if the relaxation time is little of the mixing time, then you have cutoff. So this was first proved by Diaconis and Salofkos for a different metric, not total variation, and then by Ding, Lubetsky, and myself for total variation cutoff. And both papers relied on a very special property of birth and death chains, beautiful property discovered by Carlin McGregor in '59, which is the hitting time, the time to go from left to right or from the left to any vertex here, as an exact expression as a sum of independent geometric variables. And the parameters of the geometrics is just the eigenvalues of the chain. Really a nice, exact stochastic identity. And when you think of hitting time from here to here, well, it's obviously a sum of this time and this time and this time, but these are not geometrics. And these, these are not as nice. So this representation is more subtle. And this was used in both of these papers, and this breaks down the moment you move out of birth and death chains. So, however, one natural thing is that we conjectured after this is that this should still be true when you have a tree set up. So you remember this Aldous example was based on the fact that there were two very distinct ways to get to your target. In a tree, there's only one way. And so one natural conjecture is that this extends to trees, and this now we can now prove. So the mixing time, T mix epsilon minus T mix of... So here's a general statement about trees, but I'll explain how it follows from a more general statement in a moment. So for any, but here's one theorem. So for any lazy Markov chain on a tree, you have a universal constant C here, so that the gap between T mix epsilon and T mix 1 minus epsilon is bounded by this quantity. So the geometric mean of T rel and T mix. Okay? So there are no assumptions here besides laziness and the fact that this is a random walk moving on a tree, so it moves nearest neighbors on the tree, but the transition probabilities are arbitrary. Okay, so this is always true, but if you are in a sequence of chains with the product condition, so if the relaxation time is little o of the mixing time, then you see that this geometric mean is also little o of the mixing time, and so you have cutoff. This immediately gives that on trees, the product condition implies cutoff. And it actually it's done with sharper dependence on epsilon than the previous works. But let me say, again, you can ask, is this term sharp? This geometric mean? And yes, already for birth and death chains, there are examples where you need the geometric mean. In most examples, like in the hypercube, you just need, the window is just the relaxation time. And in most examples, the relaxation time will do, but not all. So even for birth and death chains, we have examples where the window is this geometric mean. So it's sharp.
And this log epsilon means sub-Gaussian decay if you scale things in the window of the cutoff.
Right, so the log epsilon depends is also sharp, but I won't go into it. And so where does this come from? It comes from the fact that on trees we can understand hitting times much better than on general graphs, and so it comes from a more precise relation of mixing and hitting. So now I'm going to leave trees for a while and kind of get to what's under the hood. So the same way as we define T mix of epsilon, we can define hit of epsilon. So what is this hit alpha x of epsilon? So we fix alpha, think of alpha equals a half. So we're looking at target sets of measure half. And we want to ask not for the expected hitting time, but really for the tail of the hitting time distribution. So we want, so this hit of epsilon is the first time so that the probability you haven't hit A is less than epsilon. So instead of measuring distance in total variation, we're measuring the probability we haven't hit this large set exactly. And we're maximizing over the starting point and over the target set, as long as it's a big target. Okay, so let's see. There's an easy spectral argument that says that if you start in stationarity and you want to hit a large set, then then it's controlled by the relaxation time. So you get a bound which is exponential times. So the probability you take s times the relaxation time decays exponentially in s. But that's when you start at stationarity. But this allows you to easily control hitting times or mixing times. This is not the interesting direction. So if you control the mixing time, well, the probability that you take a long time to hit this set is certainly bounded by, well, so if I wanted to hit the tail to be bigger than, the hitting time to be bigger than t plus this 2s Trel, I can just wait for time t so that the distance to stationarity is small, and then I have a bound on this distance, and then with the remaining probability I can think of myself being at stationarity, and then there the hitting time is small just for spectral reasons. So it means we easily can control hitting times by mixing times, but that's not the interesting direction. This is really for completeness. And the interesting direction is the other bound that I want to emphasize more. So let's look at, so T mix of 2 epsilon, okay, it's bounded below by a hitting time, but let's focus on the interesting thing, which is the upper bound. So it's bounded above by the hit half of epsilon. So remember, this means the maximum over all sets of measure at least half and all initial states of the time needed to ensure you hit the set with probability at least 1 minus epsilon. Okay, it's a mouthful. But this is what this means. And then there's a correction term which involves just the relaxation time with a log epsilon. So in the case where the product condition holds, this is a negligible term to the mixing time and the hitting time. So, and note there's no constants here. So there's a 1 here. Okay, so this will allow you to show cutoff using control of just hitting times. Okay, so I want to explain the key ideas that go to the interesting inequality here. Let me first state abstractly, what this implies. So we have an equivalence between cutoff, which we want to understand. So the second thing is hit alpha cutoff for some alpha in half 1 and the product condition. So what I said, if you have the product condition, then you could take the alpha in the target to be arbitrary. But if you don't have the product condition, I need to still require alpha to be in 0.5. Otherwise, I have this kind of two-click issues. Okay, but anyway, this is the abstract theorem. The key to this theorem is really this inequality. So where does this inequality come? Before this work, all the estimates relating mixing and hitting were based on an idea of Aldous using, in a very clever way, stopping times. But now that somehow inevitably led to loss of constants. And now we have a different technique based on maximal inequalities. And this is what I want to kind of publicize. So here's, so again, notation. So P is a matrix, so you can think of it as an operator on functions. So P to the Tf is just the expectation of f t steps into the future. And and then we have E with respect to pi, variance with respect to pi are going to come in. Okay, so this is one standard thing I just write down for notation. So as you take the indicator of a set A, or in fact any function, but here we want to take the indicator of a set and see how the variance goes down in time. Well, this is governed by the second eigenvalue. So in other words, remember that 1 over TREL is a spectral gap. So this is just the standard spectral formula for how the variance goes down. But here is something less standard. So this is an inequality going back to the 60s, but as far as I know, we in the Markov chain community haven't been using it, and now that I'm more aware of it, I found, with co-authors, several distinct uses. So this is really powerful fact. So take any Markov chain here, any reversible Markov chain. I'm going to throw in the laziness, which simplifies things a bit. And so what is the maximal function? So f star of x is so we take p to the kf, this multiple, and we maximize over all k into the future. Okay? So this is a much larger function, but it turns out not so much. So if we take any p bigger than 1, and we take the LP norm of this, then it's bounded by q times the LP norm of the original function. So remember, if you take a fixed time, then the operator is a contraction in any LP space, so the norm always goes down. But here, we're not taking a fixed time, we're maximizing over all times, and we only lose a constant, and the constant is not too bad. So in this work, we just need to take p equals 2, but in other places, we need p more subtle. And here, so for p equals 2, what this means is the L2 norm of this maximal function is just bounded by twice the LP norm of the L2 norm of the original function f. It's quite remarkable. So this was first proved by Stein in 1961 with a worse constant, and then Norton Starr proved this in 66 with this right constant and the martingale argument. Now his theorem is much more general. So in our paper we added, a short proof which is basically extracted from his paper of just the inequality that's needed. It fits in less than a page, but I won't do it here. So but I do want to explain how this gets used. Let me just quickly mention that we have with different co-authors really two soda papers where this inequality is the key tool. So one is this one I'm telling you about, and the other one I mentioned in the abstract, probably won't have time to go into, which is bounds for surprise probabilities for Markov chains. Okay, so how do we use this inequality? So let's write sigma s just for the natural bound of the standard deviation of the indicator of A when we move to time s. Okay, now let's look at this set G with a set of good starting points for A. So in what sense are they good? So these are starting points G, so that when I look at time s or later, then the probability PGS of A minus pi of A is less than these 4 standard deviations. So if I just had S here instead of S tilde, this would be kind of immediate from the standard spectral theory. But it turns out it's very important that we have this control for all S tilde bigger than S. So first I can always make this definition, and when I say it would be immediate, what do I mean? If I just had S here, then the set G that I define this way would be huge. It's easy to see. But because of the maximal inequality, this set will still be large when I have this much sharper restriction for all S tilde bigger than S. So if we want this precision to be epsilon, then we should make this sigma s small enough, so we take s to be TREL times log 4 over epsilon, and that's enough here to get that precision. Okay, so this is the time s will take, and then we'll get this property. And the key thing is that G is large. G has more than half the space. So this is something, my point is, if I didn't have S tilde here, I just had S, this is easy. But the fact that it's true with this S tilde, which is important, where the maximum inequality gets used, and this is the whole proof. So you look at this function fs, which is the push. You take the indicator of A, subtract its mean, and push forward s time steps. Okay, so this is a function f that depends on s. And now the bad set, the complement of G, if you think about it, is exactly the set where the maximal function, not of f, but of fs, the maximal function of this should be bigger than 4 times the norm of fs. That just follows from the definition where we have this maximization for all s tilde bigger than s. And then Starr's inequality tells us that, well, first of all, use Markov inequality to say the probability of this is bounded by the norm squared of this divided by by this squared, and you get the bound. So the probability of G complement is even less than a quarter here. Any questions?
Okay, maybe an embarrassment. Can you tell me again what you required from the Markov chain here? Because there are no parameter. I always expected to see some number related to the Markov chain appearing here. That's not appearing in the Starr's inequality. So what did?
That's the key.
Right. So what you needed lazy?
I assumed lazy and irreducible and reversible, and that's it.
Yeah, but lazy is not crucial. You can double the constant otherwise. So the way that it's phrased, you can get it in continuous time without any as it is, and then for discrete without laziness, then you have it for even times.
Okay.
That's the mathematical argument. So you can get odd times by multiplying the constant. Laziness avoids that.
Okay. And to make sure I'm getting the norms right, these are not normalized by the stationary distribution?
They are.
Oh, they are. Okay.
Yes.
Then I'm happier.
So-
okay.
so all the norms
infinity
are-
norm was divided by the stationary distribution, the 2 norm, take everything.
So there's no infinity norm here.
There was on the previous side if I made p equal to infinity, right?
No,
That's
p was
the one
p was finite. P was bigger than 1 and strictly less than infinity. And on the right-hand side, yeah. So this is, but okay. So the infinity norm case is not interesting here. But so think of the L2 norm is what we want here. Okay. So this is inequality. This set is large. So how does this get used? So I claim that T mix of 2 epsilon is less than this hitting time plus this correction term. Okay, so remember the definition of G and the definition of S. S is T rel times the log of 4 epsilon. So first look at T, which is this hitting time. Because this set G is bigger than a half, I know that I'm very likely to hit G by time T. Okay? In fact, the probability this fails is epsilon. It's most epsilon. So now we want to show that T plus S is a good bound for the mixing time. So we want to compare for any set A, the probability of A at time T plus S compared to pi of A. So how can we bound this? It's in fact enough to bound it from above for all sets A, even without the absolute value. So how do I bound this? I look at 2 cases. One case is that the set G has taken me an inordinately large time to hit, bigger than T. Well, this is very unlikely. This is less than epsilon just by the fact that G is large, it's bigger than a half, and the definition of T is large enough so that any set is that large is going to be hit by probability with probability at least 1 minus epsilon. So we know this is controlled by epsilon. And the other possibility is that I have hit G by time T, but I don't know exactly when. Sometime less than T, right? And now my target time is T plus S. So how much time do I have left from my hitting time of G to the target time? Well, it's something, at least S, I don't know exactly what, but the maximal inequality or the definition of G exactly controls all times S tilde bigger than S. So whatever time I hit G in, if it's less than T, until t plus s, I have some remaining time, which I can think of as an s tilde bigger than s. And this hitting point I think of as g. And then, but now I know that from g to, in this remaining number of steps s tilde, I'm very close to stationarity just by the definition of capital set capital G. So that's it. This is bounded by epsilon, this is bounded by epsilon, so this total is bounded by 2 epsilon, and this was true for any initial point x and any target set A. So maximizing over these, I just control units of 2 epsilon, and we have, this term is here, and this term was here. So that's how we chose. So in other words, this S, right, S was chosen here to be this, and large enough to ensure that this term is less than epsilon. Okay? Any questions? Okay, so this is the key general inequality, and now I can just quickly explain, why is this used for trees, and how is this used for trees. So I won't go into that in great detail. So there are two things that help us in trees. One is we can identify essentially what are the worst sets to hit, which in general is hard. But for trees, there's always a central vertex. So let's maybe start in the birth and death chain. What's the hardest set to hit? It's very easy. So the hardest starting point is one of the endpoints, either the left or the right. I have to test both of these. And say if I start from the left, then the hardest set is just, this. So I just take enough where this is large enough to capture half of the stationary measure. So really, in the birth and death case, I just have two candidates to check. Either I start from the left and it's the right half interval, or I start from the right and it's the left half interval, and one of these is the worst. Pretty easy to show. Now, there is an analog of this for trees. So every tree has a central vertex. So let's see a picture. I don't have it here. Okay, so maybe, okay, here's the picture. So what's a central vertex? A vertex, when you remove it, then all the connected components that result are less than half the tree in stationary measure. So remember, stationary measure here is just proportional to the degrees. So in other words, when I remove the vertex and now count edges in each of the resulting components, they're less than half the original trees.
We also consider weight.
Okay, just so this is for that's a good point. So this is for trees which are with uniform weights, but of course the point of the theorem is doesn't apply just to these trees, but to all weighted trees, and then the stationary distribution is given by those weights. So there's always a central vertex. That's a easy combinatorial exercise, and there are at most two. So, and they're neighbors. So you can always fix one called O, and that's the root, and basically the worst set to hit is always what's hiding behind the central vertex. So if I start from some node, then I'm in some component, and when I remove the central vertex, I have all the other components in front of me. They should be at least a half, and up to a small correction, that's basically the hardest sets to hit. And so that's one thing we know. And then the time to hit that set is controlled by the time to hit the central vertex. So now we've reduced the problem of hitting an unknown set to hitting a specific vertex, which is general much easier. And on trees it's even easier because I know that my path to a given vertex is a specific path. So the way I get there is just summing the times along the path. So it's basically a one-dimensional situation which can be controlled. Now there's one more point I want to say about that, which is here is a central vertex and here is some vertex that I want to go from. And suppose that this stationary measure hiding behind this vertex is already substantial. then I want to say that the hitting time from here to here is small. And the reason is that the hitting time from here to here is bounded by the hitting time from an average point on this set. And we already discussed that if you start at a large set, the hitting time, the mixing time, the hitting times are all controlled by relaxation. So this is again using the tree structure. Okay, and maybe I'll skip the rest of the details for the tree and go beyond trees. So in this technique, we can go beyond trees and allow for chains that have some rough tree structure. For instance, suppose you have fixed some constant r and you're only jumping distance bounded by r, then the theorem still holds that when you have the product condition, then you have cutoff. So this wasn't even known in the case of a one-dimensional chain. So the methods before were so sensitive that they really depended on the nearest neighbor. But now we know that if your jumps are bounded by 5, and there's some lower bound in the transition probabilities within this distance 5, then you have cutoff when you have the product condition. One kind of big challenge is to understand how far this can be weakened. So one possibility is that really the origin of cutoff is in approximate tree structure in very general chains, but we don't know that. So here we have something. So expansion of small sets or escape time from small sets together with relaxation time really bounds mixing. So here is one inequality close to what I wrote before, but not exactly the same. So here, the point is, here I'm looking at hitting time of the complement, hitting time of very large sets. So it's really escape time from tiny sets. So I can control the mixing time by a combination of two things. One is the relaxation time, and the other is the escape time from tiny sets. This is something we didn't know before. And so this is the last slide. So in general, so here are some challenges here. Can you understand what are the worst sets to hit in a more general or other settings? So for instance, when you have a partial order, are these sets monotone? We don't understand that. Are the hardest small sets to escape balls? Well, the answer is no, but is it roughly true? We don't know. Maybe under some strong assumptions on the chain, say transitive graph. When it's not always true, but in many cases, the worst case the hardest sets to escape are spectral, given by the second eigenfunction. Can you characterize, when that is the case? Okay, thanks for your attention.